Before we dive into the details, I want to outline our main objective for today. Our journey begins with explain the concept of metallic bonding and the electron C model to understand how metal hold themselves together. From there, we will look at the general properties of metal and see how this characteristic relate or contrast with silicon. The core of our technical discussion will focus on band theory. We'll be explaining the critical difference between the valence band and the conduction band, and why the band gap is the defining feature of semiconductor. Finally, we will explore how can engineer silicon through a process called doping to create N-type and P-type materials. By the end of this video, you will exactly see how these microscopic bonding concepts make our modern electronic world possible. Silicon is a unique metalloid that sits at the center of modern technology, powering everything from solar cells to the computer chips in our pockets. Its versatility comes from a blend metallic and non-metallic properties in its crystalline form. Each silicon atom is locked into a stable lattice through 4 strong covalent bonds. However, to understand how it actually conducts electricity, we have to look at the band theory. This theory tells us that electrons exist in 2 states, the valence band, where they are bound to atoms, and the conduction band, where they are free to move. The forbidden zone between these 2 levels is the band gap, and it is that specific gap that gives silicon its semiconducting nature. As we will see later, by adding tiny amounts of impurities through doping, we can manipulate this gap to create electronic switches that drive our digital age.
Firstly, we need to know what metallic bonding is. Metallic bonding happens between metal atoms, unlike ionic bonding, which joins non-metals to metals, and covalent bonding, which joins non-metals to each other. In metallic bonding, a large number of metal atoms are bonded together in a bulk structure. Instead of sharing electrons between just 2 atoms, metals share their valence electrons with thousands of atoms at the same time. These electrons are not fixed in position, they are delocalized, which means they can move freely throughout the metal. So, a metal can be described as an area of positive ions surrounded by a sea of electrons. The metal is held together by a strong attraction between the delocalized electrons and positively charged metal ions. There are 2 main factors for the strength of metallic bonding. Firstly, it is proportional to the number of valence electrons. Secondly, it is inversely proportional to the size of the atom. In metals, the metal cations are fixed in a crystalline lattice structure. These positive ions stay in position and form the rigid structure of the metal. Surrounding these cations are a sea of delocalized valence electrons that moves freely throughout the entire structure. The fixed position of metal ions allow orbital overlap, which provides a continuous solid structure for electrons to travel along. Now, let's take a look at the metal properties. First, electrical conductivity. Metals are good conductors of electricity because the electrons are free to move around. When electricity is applied, electrons flow easily through the metals. Next, high melting and boiling point. Most metals need a lot of heat to melt or boil. This is because the attraction between positive metal ions and the free electrons is very strong, so it takes a lot of energy to break those bonds. Another property is thermal conductivity. Metals are also good at conducting heat. The free electrons transfer the heat quickly through the metals. Another important property is malleability and ductility. Malleability means metals can be hammered into thin sheets, and ductility means it can be stretched into wire. This happens because the layer of metal atoms can slide over each other without breaking, thanks to the electron C model. Lastly, metallic luster. The electrons in metals reflect light. When light hits the metal surface, the electrons absorb and re-emit it, making the metals look shiny in appearance.
What is band theory? So band theory is delocalized electrons that are able to move freely through bands formed by the overlapping of molecular orbitals. So metal conduct electricity with the help of their valence electrons present in them. So when there is a free moving electron, electricity can be conducted. So band theory gives us a way to understand conductivity even better. So there are three important bands that we have to know in band theory. The first one is valence band, the second one is conduction band, and the third one is band gap. So I'm gonna talk about the difference between valence band and conduction band. So valence band is the energy band that has the energy level of valence electron. Meanwhile, conduction band, it has the energy level of free electrons. For valence band, the energy level of electrons are lower. Meanwhile, conduction band, they are higher. So for valence band, they are completely filled or partially filled with electrons. Meanwhile, conduction band, they are empty or partially filled with the electrons. For valence band, electrons leave the valence band when external energy is supplied to them, while conduction band, the electron reaches the conduction band when they are supplied with external energy. For valence band, the electron density is high, meanwhile conduction band, they are low. Moving on to the band gap. So what is band gap? So band gap is the distance between the valence band and the conduction band. So the minimum energy needed to excite an electron up to a state in the conduction band is represented by the band gap. The size of the band gap is an indicator to differentiate between conductors, semiconductors, and insulated. Moving on to the formation of energy band. So it forms when a large number of metal atoms are packed closely together, causes their atomic orbital to overlap. This overlap causes the formation of energy bands.
The figure shows the band gap between the conduction band and the valence band for silicon. The gap for a semiconductor is smaller than an insulator but bigger than a conductor. Semiconductors work best in high temperatures as it enables electrons to excite and jump from the valence band to the conduction band. Semiconductors can work in room temperature as the minimum amount of energy needed for the valence electron to be excited is 1.1 eV. The moderate band gap that semiconductors have allow the conductivity to be controlled. The figure shows the formation of diamond cubic crystal lattice of silicon atoms bonded by covalent bonding. This is possible because silicon has 4 valence electrons that allow each atom to share electrons with its neighbors. When arranged in a crystal lattice, the atomic orbitals of the silicon atoms will overlap and a band gap will form. There are two types of semiconductors, intrinsic and extrinsic. An intrinsic semiconductor basically means the element is chemically pure, in this case silicon. As seen in the photo, the silicon has no extra or fewer electrons. It is fully filled, which explains why they lack free charge carriers. When the temperature is at 0 Kelvin, the semiconductors will act as an insulator. The valence band is full and the conduction band is empty. When at room temperature, some of the covalent bands may break that will generate the free electrons to move in the conduction band. However, it will have low conductivity since they have very few charge carriers. For the extrinsic semiconductor, it basically means they already have impurities added into the element to increase conductivity. Silicon naturally has a limited number of charge carriers. It has to go through a process called doping, which means it has to have elements that have fewer or extra valence electrons added into it. The doping process will be explained in the next slide.
Next, we move on into doping. So what is doping? Doping is the process of adding very small amounts of foreign atoms into the crystal lattice of silicon to change its electrical properties. Pure silicon has limited conductivity, so doping is used to increase the number of charge carriers. By controlling the number of valence electrons, doping creates defects in the silicon lattice. These defects cause an imbalance, allowing electrons to move more easily, which increases electrical conductivity. Elements from group 3 and group 5 of the periodic table are commonly used. For example, boron, a group 3 element, produces a p-type silicon by creating holes, while phosphorus, a group 5 element, produces n-type silicon by supplying extra electrons. These p-type and n-type materials form a p-n junction, which is the basis of semiconductor devices such as diodes and photodiodes used for light detection.
Now, let's take a closer look at n-type silicon. This material is created by doping the silicon lattice with a group 15 element, such as phosphorus. Because phosphorus atoms have 5 valence electrons compared to silicon's 4, an extra electron is introduced into the system for every phosphorus atom added. This extra electron is not needed for bonding, so it is free to move, which significantly increases the conductivity of material. In n-type semiconductors, these electrons are the maturity charge carrier. Due to these properties, n-type silicon is fundamental building block commonly used in the creation of diodes and transistors.
Next, I will explain about p-type semiconductor. A p-type semiconductor is a form of silicon and is one of the most commonly used materials in electronic devices. It is formed by doping pure silicon with group 3 elements such as boron, which have one fewer valence electron than silicon. When a boron atom replaces a silicon atom in the crystal lattice, it is unable to form 4 complete covalent bonds. As a result, a hole is created. This hole represents a localized deficiency of an electron and can move through the lattice as nearby electrons fill it. P-type silicon is called P-type because it contains an excess of positive charge carriers, which are the holes. These holes act as the majority charge carriers, while electrons become the minority carriers. As shown in the diagram, the presence of holes allows electrical current to flow through the material, making p-type silicon essential in the formation of p-n junctions used in devices such as diodes and transistors. To conclude, we can see clear differences between metals and silicon based on their bonding models. Metals rely on the electron C model, where electrons are free to move, while silicon forms a rigid covalent lattice, giving it different physical and electrical properties. In terms of band theory, metals conduct electricity because their valence and conduction bands overlap. Silicon, however, behaves as a semiconductor due to its 1.1 electron volt band gap, which acts as a controllable barrier to electron flow. Unlike metals, the conductivity of silicon is tunable. Through the process of doping, we can precisely control its electrical behavior by creating n-type and p-type semiconductors. This ability to control the band gap and conductivity is what enables the formation of the p-n junction, which is the foundation of modern electronic devices such as transistors, solar cells, and ultimately the digital technologies we rely on today.